All right, welcome. This is Chapter 11, Section 4. And so what we're going to be doing today is we're going to be talking about wave interaction. Okay, so in this section, our objective is to apply superposition principles. So a superposition principle is a combination of two overlapping waves. So when two waves interact, they can either be constructive or deconstructive. The difference between those two is a constructive wave is where two waves are coming in the opposite direction, and as they come together, they combined. And after they combined, what happens is then they're going to go in the opposite direction. When added together, the resultant wave is larger than the individual displacement. So that is called constructive interference. The other one that you would learn in here would be destructive interference. And as you can tell here, you have one wave that's at the medium on the top in the positive direction. You have another wave that's coming underneath in like the negative direction. And so what happens is if you look, you can see the magnitude of this one compared to this one. And as they come together, they no longer combine together. They actually go and they do the difference of the two troughs themselves in opposite directions. And as you can tell by the drawing here, that you can see that this wave here is going to go back in that direction and in the opposite direction. And it says all the instant of the two pulses overlap, at the instance of the two poles overlap, they completely cancel each other out as if their waves were not disturbed at all, or actually interfering with each other. Okay? So the second thing that you were supposed to be able to do in this section is to tell me the difference between a constructive and deconstructive wave. So here's my constructive wave. They combine together and they get larger than the original waves. Deconstructive is where they have the difference and they cancel each other out. The other thing that you would need to know about waves that we will be talking about is we're going to be talking about what deflection is. Okay? So when we're talking about deflection, we're talking about that a wave is either hooked to something, a fixed boundary. So here, first of all, we'll show you where you have a travel pulse that it goes down the rope in the end of a free sliding up post. So here we have a rope that's attached to a pole, okay, and it is able to slide up and down this pole. So what happens here is as the wave comes here, and as you can tell, it comes this direction, and then when it goes to the pole, it goes up. Then it comes back down, and then it travels in the the opposite direction on the way back. So that is when we're talking about reflection of a pulse wave, and we have what's called an incident pulse, and we have a reflective pulse. An incident pulse is when it's going toward the pole, and a reflective pulse is the pulse that's coming back from that. Also, we also have it where we're talking about something that is like fixed to a wall. So these are two different variations of it. One is where it is a rope tied around a substance that can slide up and down. And the other one is where it is going to a fixed position. And as you can tell here, you still have another impulse. It goes here, and then when it comes back, it goes down, and that is known as the reflected pulse. The last thing that you would need to know about this section is what's called a standing wave. Okay, so we have an oscillator at our school that if you were able to turn that oscillator on, you would be able to create waves, and as you created those waves, what that would do is you would have two waves that are going on a string together, and eventually they come together and they have what's called like notes. Okay, so as that thing is vibrating in a way, what happens is that it vibrates so quickly that there's more than one wave at a time. So if you look at page 391, you would see kind of what they would look like. You also would see a diagram of that on page 391. And then also on 392, you would also see that diagram. So what I have done is I have drawn that in my book here. First of all, the first thing that I did was I defined what a standing wave was. It is a result wave pattern that appears to be stationary on a string, alternating construction and deconstructive waves. When you look here, you have your antinode, which is here, and then your node is where they meet together. Okay, an antinode is the point of a standing wave halfway between two nodes, the largest displacement, and then a node is a part of a standing wave that is maintained at zero displacement. And that is the end of chapter 11. But before we get finished with chapter 11, what I would like to do is I would like to do a little bit of a review on what we've talked about in chapter 11. Chapter 11, of course, was talking about vibration and waves. The first thing we started with was simple harmonic motion. And then when we were talking about a simple harmonic motion, we were talking about where we have the maximum displacement, we have what's called an equilibrium position, we have a maximum displacement, we have an equilibrium position, we have a maximum displacement, and what it basically is talking about there is it's giving you the information of something that is moving. And it gave us two separate things to look at. One was something hanging, right, from a fixed area. And that one here was just a rope like we've seen before where we talked about pendulums before. If you remember when we were talking about pendulums, this conservation of mechanical energy is where you have a bob or a mass that is on the end of a string and that it goes back and forth where you change from potential to kinetic energy. Then what we did is we went and we applied that same information to a something that is attached to a spring. And they gave us different types of formulas for that. And that was for section 1. If you the picture that I took that I actually put in my book was on page 373, and it was just basically showing you the difference between a pendulum and a fixed object on a spring. When we got finished with that, we went into section 2, which is your measurement of simple harmonic motion. When we're talking about that, there's some keywords that you would need to know. Amplitude, period, and frequency. Amplitude is the maximum displacement from equilibrium. A period is the time that it takes to complete a complete cycle. And frequency is the number of cycles or vibrations per unit of time. And so what I did in my book is on 375, I just copied the graph the data table that they have here, actually showing amplitude, period, and frequency in a pendulum situation, what the definition would have been, and what kind of units of measurement that was in. Then I actually wrote down what a period is, which is, of course, 2 pi over the square root of the length over the free fall acceleration. So that is the formula that you use for your sample problems, which were on page 377. So on 377, if you need to look at that again, there's videos showing you how to do the math as far as those 4 questions on that page. And then after that, we also had something to talk about the period of a mass spring system in a simple harmonic motion, which we had an example explaining to us the simple harmonic mass of a spring system, mass spring system, and how to do that. And that was going to be T equals 2 pi square root of M divided by K, which equals 1 over F. And on those problems there, I went over questions 1 through 3 as far as what the math goes for that. The main thing that you have to do is you have to read what the question is asking you. Like, for example, number 1 says a mass of 0.30 kilograms was attached to a spring. That's my mass. And it was in motion with a period of 24 seconds. That was my time. And it was asking us for the spring constant of that. And so what we did is we took our formula, which is our 4 pi squared over mass over time squared. So the only thing we did here is we just went through and we just plugged in what we have. We have mass and we have time. So we did 4 pi squared times 0.30 kilograms over 0.24 seconds squared there. This here, if you have another question about it, go back to the video where it was talking about 0.2. And then yesterday, you were talking about the different parts of a wave and the properties of a wave. The main one, which was the medium. The medium is what that substance is traveling through. Now, that substance can travel through air, can travel through water. It's the median is what it's traveling through. Mechanical waves are waves that require a medium through which it travels. There is a pulse wave, a periodic wave, and a sine wave. These are 3 different types of waves. When we're talking about a pulse wave, that is just one single pulse. That means just like one rope going back and forth. A periodic wave is where it's going in a sequence. And then your sine wave is a simple harmonic motion. And it actually shows the curve as you plot it. And then it was talking about displacement. When we're talking about what a transfer wave is the direction of the wave that's traveling. If you remember, when we were doing that, we have to kind of like diagram our wave. Remember, our amplitude can be from crest to crest or trough to trough. When we're talking about displacement, and crest is the highest point, trough is the lowest point, and the wavelength is one complete cycle. That is what's called a transverse wave. A transverse wave, of course, goes up and down. When you're talking about a longitudinal wave, that's more of a wave that is going kind of like a slinky does, where they are getting compressed and then they stretch and then they're compressed again. That's a longitudinal waves. Longitudinal waves are particles of a medium vibrating parallel to the direction that's traveled. Sound waves, air particles vibrate, and then your sine curve is the density of the wave of the compressed wave. And as you remember, density, we're talking about period frequency of wave speed again. When we're talking about wave frequency, is the number of waves that pass at a given period of time. A period is one complete cycle, and the speed is the frequency times the wavelength. And then we had some math problems yesterday dealing with those. So like for question number 1 was saying a piano emits a frequency with a range of 28 hertz and a high of 4,200 hertz. Find the range of the wavelength of the air obtained in an instrument when the sound waves is on 340 meters per second. I'm on page 385. So what you're going to do there is you're going to take what you have here. So our frequency 1, it says it starts at 28 hertz, and our frequency 2 is 4,200 hertz. And then we have to find the volume or the speed at 340 meters per second. So what you're going to do is you're going to have to find your lambda 1 and lambda 2. To be able to do that, you're going to take your velocity over your frequency 1. So you're taking your 340 and you're dividing that by your 28 hertz, and that's where you get 12 meters from. And then your lambda 2, you're taking your 344 divided by your 4,200, which gives you your 0.081 meters. And then you do the same thing for number 2 and number 3. This is just a kind of a quick review today, because you will be taking your test tomorrow. And so I want to make sure that you are kind of prepared for your test on Friday. As you can tell, I'm feeling a whole lot better. So I just want to make sure that I gave you the information that you needed today to help you out. I hope you have a good day. And just remember, the test is tomorrow. God bless.